After conducting the qualitative analysis of the Solow's growth model, now we can do its quantitative analysis as well. So let us start the quantitative analysis of Solow's growth model. For that, we assume that the functional form of the production function is Cobb-Douglas, and it is also linearly homogeneous. It means that if you introduce a scalar, the factoring out will give us that scalar with power 1. For example, if we introduce lambda, the factoring out will give us lambda raised to the power 1. So this is another thing which is a basic property of Cobb-Douglas production function. However, our concern is to use it here, and here it's the functional form where labor and capital, they give rise to a certain level of output, giving rise to this function of the production. Now we know that in the Solow's growth model we have a knack of using small k, which is actually the ratio of capital and labor. So to develop that, we can take labor as a common, and when it comes out, instead of labor 1 is left, and since there was no labor in this, it is now capital over labor. Now 1 is a constant which is not written in constants, only variables, functions, only variables are written in the functions. So we exclude this 1, and this k over L can be written as small k, and in terms of k and L, we have written a new function that is now in terms of k, that is phi of k. Initially it was f of k and L. Now since the variable has changed, it is now small k only. So instead of f we use phi, an alternative, to show that the variable has changed, and labor is also there outside getting multiplied. Now this was the functional side. What about the exact equation? We know that this is the form of the Cobb-Douglas production function. It is possible because if alpha and beta are the powers of capital and labor respectively, the value of beta will be 1 minus alpha. So if 1 minus alpha is here, if we can write it instead of beta here, and that's what you can see, that the power of labor is not beta, it is 1 minus alpha. This will create ease for us because we won't be writing beta again. We'll be writing one parameter, that is alpha, and that will help us to keep the thing simple and finally come up with a certain equation of the differential kind that we will see as we go ahead. Now we can break this into two terms, that is labor and labor power minus alpha, and then we can gather the alpha containing terms, that is capital and labor. So this will be the capital and labor terms, and labor will be here. The purpose of writing them together is to make a whole power of it, and when we write a whole power we get small k. Small k is the ratio of capital and labor, where the labor remains outside. So if we compare these two outcomes, it shows that instead of phi k we have small k alpha, because you can see labor is here on both sides, whereas phi k is there for k raised to the power alpha. So instead of phi k we have k alpha. So phi k is now evaluated, which was not evaluated before when we developed the qualitative analysis of the Solow growth model. Now we have this first order differential equation, which we have already seen in the qualitative model. So now the value of phi k is substitutable, and we are going to put it here. So when we put it, it becomes like this, and then we can see that this is the rate of change of capital per worker over time, because this dot shows this, and we have k with power 1, and we have k with power alpha. So this will help us to anticipate that we are going to get a Bernoulli equation. So let's rearrange it, because this is the term with some power other than 1, and let's shift it to the right hand side, and this k with power 1 should come on the left hand side. And we can write this k dot as rate of change of capital per worker over time. Rearranging these, we get this form which is adjacent to the Bernoulli's equation, and we can see instead of m we have alpha, instead of y we have k, instead of t we have s, instead of r we have lambda. So alpha is not equal to 1 because, you know, if alpha becomes equal to 1, then 1 minus alpha, that is 1 minus 1, will be 0, which means that the power of labor will be 0 and labor will be removed from the equation. And this is something we do not do in the Solow's growth model, because Solow growth model, unlike the Domer's growth model, includes the labor variable explicitly. So alpha cannot be equal to 1 here, because this will reduce the power of labor to 0, and definitely labor will not remain a variable with a power of 0. So in order to retain labor in the given equation, alpha is not equal to 1, which means that m is not equal to 1 and it's a Bernoulli equation. And also labor cannot have the power of 0, because if it is 0, it means that the power of alpha will be equal to 1. So already alpha is proven not to be equal to 1. So when alpha is not equal to 1, it means that labor will also be not equal to 0. So both of the possibilities are dropped, which means that we have a Bernoulli's equation, and we have extracted these values just like we usually do, and we can note these values here. By using these values, we can linearize the given nonlinear differential equation of the Solow's growth model. You know that this is the standard form of the Bernoulli's equation that can be linearized into this form, and when we linearize it into this form, we can solve it by using the usual method of first order linear differential equation. So these are the steps that are undertaken in order to convert it. We know that this is the standard way of writing the Bernoulli's equation, and what we can do is we can put the values. As you can see that instead of y we have now z, and instead of 1 minus m and 1 minus m here, and this r and t, we are substituting values. Instead of m we are writing alpha, instead of r we are writing lambda, instead of m we are writing alpha, and instead of t we are writing s. So if we substitute these values, linearized form of Solow's growth model differential equation will come into being, and this is that equation. Now in this equation we have alpha and we have small s and all these relevant variables. Now this can be solved by getting it transformed into a derivative form, which is very usual, and we can easily solve it. So dividing it by dt, we are going to get the relevant form. So we divided it by dt on both sides. On the right hand side there is no effect, however on the left hand side we have got this term. Now this term is now being simplified and being written in a way which is adjacent to the first order linear differential equation. Now 1 minus alpha can be multiplied with this term primarily and with this term, that is s. So we multiplied it on two sides, and now we are in a position to say that z is that variable, the derivative of which is here, and then z is there with power 1, and this is a term which is a constant and contains no variable as z. So now it is comparable with the first order linear differential equation, which is here, and then we can find the value of a, and we can write the value of b, and we can substitute these values. So a is here and b is here. This is the formula of the definite solution that we have already learned, and we can put the values in it. So instead of y we have z, and instead of y naught we have z naught. Instead of b we have 1 minus alpha s, and instead of a we have 1 minus alpha lambda. And again instead of a we have this value, and instead of b we have this value, and this is the value of a. So we have substituted the value as per the given information, and these terms, that is 1 minus alpha, both in the numerator and denominator, will be cancelled out, leaving us with this, which is the time path in terms of z. However, the original function was in terms of k, so we have to resume the value in terms of k. So as we remember that in the Bernoulli's equation, the variable has the power of 1 minus m. Here m is equal to alpha, so we can write it instead of z, so k raised to the power 1 minus alpha. And this is the other side where z naught will be replaced with k naught, and definitely the power, that is 1 minus alpha, will appear here. And now we get this form of the solution now, which is in terms of k, and k naught is the initial condition. Now the dynamic stability is there. Dynamic stability should be investigated here. You can see that this is the time path, and in the time path we have the complementary function, and this is the particular integral. So the equilibrium value is this, and this is that part that we want to fade over time. This is the exponential part, which has time variable in it. So this is the time dependent part, and this is the coefficient of it, which is actually the arbitrary constant, and it is now written in terms of the initial condition and some other parameters. So we will focus on this part and see if it reduces to 0 over time. So this will remain there, and another thing that we need to understand here is the sign of the exponent. 1 minus alpha has to be understood, because this is going to give rise to the final answer. So this is the exponent beside t, and we need to understand it. We know about lambda. It is the rate of growth of labor, and it is definitely positive, and alpha is within between 0 and 1. It's a kind of fraction, so it is going to be a positive value, though it is less than 1, but still it's a positive value. So it's greater than 1 and it is still less than 1. So when we subtract it from 1, the answer will be positive, and it will be less than 1. So we will get a positive answer. For example, if alpha is, as the range guides us, it's less than 1. So if it is equal to 1.9, 1 minus alpha will be equal to 0.1. So it means that it is a positive value, and it is it is less than 1. So when it is this answer 1 minus alpha is positive and less than 1, and the lambda value, it is also positive, so positive into positive will be a positive value. So the answer of this term is positive, and we know that with this term there is a negative sign, so the power will be the exponent will be negative at the end, because the value itself is a positive value and this is the negative value. So exponential decay will happen here as the exponent is negative. Now we shed some light on the coefficient. It is basically a multiplicand of the exponential decay term. So no matter if it is positive or if it is negative, when we multiply it with the exponential term which is decaying, it is going to eat away this coefficient as well. So this thing, that is the exponential term, is going to eat away this the coefficient term as well. This means that the whole complementary function is going to fade away, and the time path will converge to the equilibrium value, that is this value, as the time passes. Now finally we have the original value of k, not the power 1 minus alpha. So we shift this 1 minus alpha power to the other side, and it becomes reciprocalized, and we get this value. So t approaches to infinity is the natural condition, because time always passes, and if we allow it to pass indefinitely, we can write it like t approaches to infinity. So finally the time path is in purely in terms of k, and now we know that it is going to converge to the equilibrium value, and that will happen because of the exponential decay. So this is the outcome, that the capital to labor ratio assumes a constant value at equilibrium. This is the constant value, and which directly varies with MPS and indirectly with lambda, which is the growth of labor. So there is a linkage between this and that parameter, and we have also understood it because s is in the numerator and lambda is in the denominator. So after explaining this, we can also see that there is a kind of appendix. Those of you are interested in linearization process of the Solow's growth equation using the Bernoulli substitution method, you can pause the video and see. And just to remind you, when we developed the Bernoulli's equation, when we did the linearization process over there, this was the equation that we did, and the substitution was quite similar. There were two substitutions, and here again we have two substitutions. However, we have k instead of y here. So in the next slide we have the substitution process both for first and the second, and then we have the linearized form of it, which is finally written here. So this is how we obtained the dz and dt terms of the linearized form of first order Solow's differential equation. And then you can numerically verify if the convergence is happening. We are assuming that initial level of capital per worker is 100, initial condition is given, and then we have MPS, marginal propensity to save, 0.2, and alpha is also there, and then lambda is also given, which is a growth rate. So we can decompose the time path, and primarily this is the exponential term, and then this is the zc in this case, or kc, because it is now in terms of c, and this is the overall time path, that is kt. So when we substitute various values of t here, we start with 0, and there are many values that we can substitute. However, the process of decay is very slow, so we chose to skip a few values in this table. However, we should use all the values. So as you can see, as the time is passing, the value of the exponential term is decaying, that is, we have exponential decay, and also the value of the complementary function is also decreasing. Therefore, the value of the time path of capital per worker is nearing the equilibrium level of the capital per worker, which is 8. So you can see the value is increasing from 4 to 8, it is approaching. So we can say that exponential decay is happening, and Kc, that is the deviation part, is also decaying, and convergence is happening, and we are getting close to the equilibrium, the value of which, symbolically speaking, is this. And finally, in economic terms, K status represents the steady state growth that we have understood in the qualitative approach video suggested in Solow growth model. So the model shows convergence towards the steady growth equilibrium. So in this way, we have understood the qualitative side of the Solow's growth model, and we have solved it by using the Bernoulli's equation method, which was capable of giving us the answer of particular integral as well as the complementary function, and then we were able to verify the dynamic stability of it as well, and it showed convergence because the value of the exponent on the whole is negative because of the negative sign of the formula, due to which the verification of the postulate given by Solow that the steady state growth will be achieved is now getting verified. It was verified primarily with the help of the diagram in the qualitative analysis, but here it is done by using the quantitative analysis, and the results are the same. That is, steady state growth happens. Thank you.